So the previous chapters have focused more on methodology, but in this chapter, we'll talk more specifically about data analysis and interpretation. And the goals here are really to talk about, does the data support our claims about behaviors? So we, of course, start with descriptive statistics to describe what's happening. If you remember, we've talked about central tendency that tells us about the average score. So here we're interested in differences in sleep habits depending on class time. So we've got the hours of sleep, which is the score. The frequency is how many participants got that score. So we've got 2 people who got 3 hours of sleep. We've also got 2 people who got 9 hours of sleep. And so we have the mean here is 6.1 hours. That's the M stands for. The N is 29. So if you add up all of these, there's 29 people in the class. We're comparing 2 hours, though we've got the 9 a.m. class versus the 11 a.m. class. And so here, again, we've got the score, the hours of sleep, and the frequency. In the 11 a.m. class, we've got one person who hasn't slept yet. We've got one person who slept 13 hours. We've got 5 people who slept 6 hours. Now, what you'll notice is the mean is actually the same. So the mean for the 9 a.m. class is 6.1 hours. The mean for the 11 a.m. class is 6.1 hours. They both have 29 students, but there's clearly something different about them. And one of the ways that we can assess that difference is through the variability. Okay, so the mean tells us the center of the distribution. Both of them have the same center. But the variability is how spread out the scores are. And the larger the variability, the more spread out the scores are. And you can see that the bottom score, the bottom distribution is much more spread out. So although the center is the same, the variability or how spread out the scores are is different. So the mean and the variance together give us a lot more information, a more complete picture of what's going on with the data. So standard deviation and variance are the most commonly used measures of variability. And we typically use the mean as the reference point to determine whether scores are generally near or far from the mean. So the goal with the standard deviation and variance is to find the standard distance from the mean. Some scores will be very low or very close to the mean, which will be low variability, while others will be far from the mean, which will be high variability. So standard deviation is the most common way that we measure variability. And standard deviation is how far is the average score from the mean. You don't need to memorize this formula. I'll give it to you, but I want you to kind of understand conceptually what it is before we go talking about interpretation. So when we talk about a deviation, we're looking at each individual score. How far is each individual or participant score from the mean? And so the x minus m is the deviation. How far is each individual score from the mean? And basically what you're going to do is square that, add all those squares together. That's what the sum means. And divide by the number of scores minus 1 and take the square root. So what does this actually look like? Why are we doing all these steps? So the mean is always the reference point here. M represents mean. Sometimes you'll see mean as X bar with a line over it, but we're going to use M for this. So the mean is the reference point. The X is each individual score. So the number is, so with a deviation, it gives you the number and the sign. So the number is how far each score is from the mean, and the sign is the direction from the mean. Is it higher or lower? So it tells us whether the score is above or below the mean and the actual distance. Okay, so if you want to find the standard deviation, these are our scores. So we've done a study. We've assessed 5 people's scores, and we've got 7, 6, 3, 3, and 1. Okay, the first thing in the standard deviation is to find the deviations. So you need to calculate the mean, and then find each score's deviation from the mean. Okay, so in order to get the mean, we're going to add them all up and divide by the number. Okay, so if we add them all up, the sum is 50. There's 5 individuals, so that makes our mean 4. Okay, so what we want to do is get the deviation, figure out how far each one of these scores is from the mean, or 4. So to get the deviation of this score, you do 7 minus 4, 6 minus 4, 3 minus 4, 3 minus 4, 1 minus 4. Okay, so here it is completed. And this tells us how much each individual score varies from the mean. Some are above the mean, some are below the mean. Okay. Now remember, our goal here, now that we have our deviation scores, our goal is to know how much, the deviation scores tell us how much each individual scores vary from the mean, but we want to know the standard or typical variation from the mean. So we want just one number to represent the whole group. Okay, so if we want to get a standard distance from the mean, kind of the obvious way is to calculate a mean of those deviation scores, right? That kind of makes sense. So let's try to do that. We've got our deviation scores that we already calculated. We go to calculate a mean, add up all these deviation scores, and the sum of our deviation scores equals 0. So our mean, and this will always be true, the sum of your deviations will always equal 0. The mean serves as the balancing point. The way we calculate the mean is that there are equal numbers of scores above or below it, or equal weights of scores above or below it. So it serves as kind of a balance point. So no matter what the mean is, the definition implies that it'll be a place, have the same place in the distribution. So if you add the deviations from the mean, you'll always get 0. Okay, so this is, the mean is the point where the scores are balanced. And so the mean of the deviations is always 0. Okay, so here's our mean. Of 4, we've got 3 points below plus 1 point below plus 1 point below means 5 points below. 2 points above plus 3 points above means 5 points above. So you can kind of think of this as a seesaw where the scores are balanced in regard to how far away from the mean they are. So we can't just take a mean of the deviations because we're going to wind up with 0. So the next question is, well, how can we make it so that when we add the distances from the mean, we don't always get 0? And one way to do that would be to make those negative values go away. And so one way to make those negative values go away would be to square the deviations. So to get the average now, we're going to square each deviation. Then we're going to add up all the squared deviations and divide them by the number of people. So this will get us an average of the squared deviations. So we can go through and do this. We've got our scores, we've got our deviations from the mean, and then we're going to score it. We're going to square it, right? So 3 squared is 9, 2 squared is 4, and so on. Now that we've got all the squared deviations, we can take a mean of the squared deviations. We no longer get a 0 when we add these up. The sum of the squared deviations, which is called the sum of squares, is 24. We can divide by the total number of people, and we get an average of 4.8. So this is called the variance, the mean of the squared deviations. But if we think about what it actually means, the variance itself is not terribly interested. We're not interested in the average of the squared deviations. We want to get back to the standardized versions to know how far away individual scores are from the mean. So we want to get it back to the original square scale. So the way we do that is take the square root of the variance. This corrects for all the squaring of all the deviations. So this gives us our standard deviation, which is a measure of the average distance from the mean. The bigger the standard deviation, the more variability in a set of scores. So here you can see we've got our score, we've got our deviation, we've got the squared deviations. So we add up all our squares. 24 divided by 5 is 4.8, but we want to get it back in that standardized measure. So we take the square root of that and we get a standard deviation of 2.19. So our mean for this set of scores is 4, and on average, or the standard deviation or the standard distance from the mean is 2.19. Okay, so that's for experimental data. A correlation, if we go back to correlational data, a correlation is the relationship between two variables. And so we've talked a little bit about correlations, and remember that correlation can tell you about the magnitude of the relationship as well as the direction. And when you're dealing directly with data, a really useful tool is actually drawing a scatter plot, because it makes it much easier to interpret a correlation. And so when you draw a scatter plot, you're going to have an x-axis, that's one of your variables, and a y-axis, that's the other. And you're going to draw a dot for each person. And correlations in general and scatter plots in particular can tell you about the magnitude and the direction. So again, magnitude is how well data corresponds to a straight line, and direction is whether that line is going upwards or downwards. This would be a positive correlation, right? Because it generally goes up. Each one of these X's represents a participant. So this person scored really low on variable X and variable Y. This person scored really high on both of these things. This is a zero relationship. There's no clear pattern. This is the negative relationship, where this person right here scored really low on X but high on Y, and this person the opposite. This is just an example of a correlation. So if you look at this, hopefully you'll see that this looks like a positive correlation, and the correlation is in fact 0.79. Here we have our x-axis is chocolate consumption, and the y-axis is the number of Nobel laureates. Okay, and in this case, their flags represents a country. So we've got 2 data points from each country. How much chocolate do they consume, and how many Nobel laureates do they have? We can see China is very low on both. Switzerland is very high on both. And then other countries rank in between. But this also demonstrates kind of one of the cautions with correlations that we need to be careful of. Can we say that consuming chocolate causes countries to win Nobel Prizes? No, of course we can't, right? So we can't make causal statements based on just a correlation. Something like wealth could be a third variable that can account for that. Okay, so we talked a little bit, and so now we're going back to experiments. And kind of a final way that we might summarize experimental data is through an effect size. And so we talked about this a little bit when we were doing an experiment, and we want to know if our independent variable had an effect, and if so, how big of an effect, and that effect size will tell us that. And Cohen's d is about the size of the difference between the levels of the independent variable divided by the standard deviation. And because it's in units of standard deviation, we can actually compare across studies. Another strategy that we talked about when we're getting to the stage of confirming what the data reveal is the confidence interval. And so we want to know kind of the confidence interval around one mean. So we've got our mean for our sample, and we want to know how likely is it that the population will fall in this range. So last time we talked about how to interpret a confidence interval. Today, we're going to talk a little bit more about how to actually calculate a confidence interval. So again, remember that the sample is an estimate for the population, and the confidence interval gives a range of scores where we think the population lies. Sometimes this is also called a margin of error, where you might see this in like election polling results. They might say, oh, it looks like the Democrat is ahead by 5 points, but the margin of error is 3 points, right? So the Democrat could be 3 points lower or 3 points higher. So the first thing we're going to talk about is a confidence interval around a single mean. Here is the mean that we got for our sample. Here's what we think the population might have. Okay, so this is the formula. And you need to get the upper limit, which is the plus, and then the lower limit. Okay, so I'm going to show you how to find T and SM in the next. But the general idea is you take the mean and then do plus or minus the T value. So T of 0.05 is the value for the T statistic where the degrees of freedom equals n minus 1 and alpha equals 0.05. And then SM is the standard error of the mean. Okay, so the T value, you're going to need to look up in this table. So it's table A2 in your book. And all you need to do is get the number and plug it into the formula. Now, the degrees of freedom, DF, you don't need to understand this concept. It's a super abstract concept, but it basically has to do with how the number of participants influences the results. Okay, and so your degrees of freedom is always n minus 1, the number of people minus 1. We're also always going to assume that alpha is 0.05. That cutoff, the likelihood of getting the results by chance is 0.05, unless it's otherwise specified. So if we had a degrees of freedom of 15, we had 16 people in our study, our degrees of freedom was 15. In order to calculate the confidence interval, you need to know that T value at alpha equals 0.05. So our T value right here is 213. Let me highlight this. Okay. So again, unless otherwise noted, you use 0.05 and you're going to find the T value for the degrees of freedom and the alpha level. So 2.13 is the T value that you need. Now note that if the degrees of freedom aren't specifically listed, so if you had your degrees of freedom should be 50, you can kind of look at these T values and take a guess, right? It's probably 2.01. That will be close enough. For low numbers, each one is listed. The other number that you need to calculate the confidence interval is the standard error of the mean. And so basically what the standard error of the mean is it measures how well the sample mean estimates the population mean. So I've given you the formula here. You don't really need to understand the concept, but it does require some basic calculations that you do need to do. So the calculation is the standard deviation divided by the square root of the number. All right, so we also have talked about using confidence interval to compare two means, right? So if we have a sample means for two different groups, we want to know, are we sure that the population means are different? If the confidence includes 0, then there could be no real difference between the means. Essentially putting the confidence intervals around two means, but statistically, we're actually putting a confidence interval around the difference between the means. So we want to know, is this difference here or could that difference be 0? So this is the difference between the sample means. If we put our confidence interval around the sample means, there's still a difference. And so this is the range of true differences between the population means. It could be as small as 1 point. It could be as big as 15 points. Right, so you're going to find the closest points and the farthest points and look at the range. And so this tells us the biggest or smallest possible difference. The population mean difference is somewhere between 1 and 15. Because a true difference is greater than 0, because the range is always greater than 0, does not include 0, what we would conclude for this is that there really is a true difference between the means. Because there is no overlap between the groups, it's never 0 or smaller, we can conclude that there's difference. In this example, we've got the difference between the sample means, which is 4. If we take a look at the confidence intervals, there's significant overlap, right? And the difference could be anywhere from -3, meaning group 1 is actually lower than group 2, up to 11, where group 1 is higher than group 2. And because the confidence interval for the difference between the means overlaps with 0, we say there is no true difference between the groups. So this is essentially the same formula as the confidence interval around one mean. So we take the difference between the two means. Okay, so here instead of just one mean, if we're looking at the confidence interval between two means, you're taking the difference of mean 1 to mean 2. You're going to look up t in the table, and then I'll give you the standard error of the difference between the means. So you won't need to calculate this. I will give this to you. So again, you're doing the same calculation, and here you're looking at, does this confidence interval include 0 or not? If it includes 0, then there is no significant difference between the groups.